The laws of physics break down on worlds far from our own. We are about to journey beyond our solar system to uncover 25 planetary anomalies that defy our understanding of reality itself. By the end of this exploration, you will see the universe as a place of limitless and shocking possibility. We will encounter planets where the sky rains molten glass and others so dark they swallow nearly all light. What do these cosmic oddities reveal about the fragile rules we think govern existence? Our journey begins with a world trapped in a gravitational embrace so intense it is being slowly consumed. Meet WASP-12b, a planet classified as a hot Jupiter, a gas giant orbiting so close to its star that a single year lasts just over one Earth day. This proximity creates a phenomenon known as tidal locking, where one hemisphere forever faces the stellar inferno and the other remains in perpetual frozen shadow. The temperature difference is unimaginable, with the dayside heated to over 4,000 degrees Fahrenheit, hot enough to vaporize iron, while the night side languishes in a deep, interstellar chill. But the true anomaly is not just the eternal day and night, it is the planet's shape and fate. The star's immense gravity does not just hold WASP-12b in orbit, it actively pulls the planet apart, stretching its gaseous body into a distorted, teardrop form. This process, called Roche-Lobe overflow, sees the planet's outer atmosphere spilling over a gravitational point of no return, streaming toward the star in a continuous, doomed river of gas. Observations from the Hubble Space Telescope have captured the spectral signatures of heavy elements like magnesium and iron being boiled off into space, creating an extended, comet-like tail of planetary material. It is a world in the process of disintegrating before our eyes, a celestial body being unmade by its own sun. We can think of it like a comet passing too close to our sun, its ices vaporizing into a glorious tail. But here the scale is planetary and the time scale, while still millions of years, is a blink in cosmic terms. This violent dance challenges everything we thought we knew about planetary stability and evolution. What does watching a planet die teach us about the fragility of celestial order? Could such dramatic processes have sculpted our own solar system in its violent youth, explaining the absence of worlds that once were? The destruction of WASP-12b is a stark reminder that the universe is not a static museum, but a dynamic arena of creation and loss, setting a breathtaking and ominous stage for the even stranger anomalies to come. If the eternal day of WASP-12b seems extreme, consider a world of permanent and perfect night. Orbiting a star 750 light-years away is a gas giant named TESS-2b, a planet so profoundly dark it is blacker than coal, blacker than fresh asphalt, blacker than any natural object we have ever found in the cosmos. This world absorbs over 99% of the light that strikes it, reflecting less than 1% back into space. To put that in perspective, its surface is darker than black acrylic paint. Imagine holding a piece of charcoal fresh from a fire. It is hot to the touch and radiates a dim glow, yet to your eyes it appears as a deep, matte black. TESS-2b is like that cosmic charcoal, a searing hot world that somehow vanishes into the void. This discovery, made by the Kepler Space Telescope, completely defied expectations. Gas giants in our own system, like Jupiter and Saturn, are relatively bright, their cloud tops reflecting a significant portion of sunlight. So what makes this distant giant so impossibly dark? Astronomers believe the answer is a toxic and exotic atmospheric brew. The planet orbits so close to its star that its atmosphere is superheated to nearly 2,000 degrees Fahrenheit. At these infernal temperatures, familiar, reflective chemicals like ammonia clouds cannot form. Instead, the atmosphere may be rich in vaporized light, absorbing elements like sodium and potassium. or perhaps shrouded in strange clouds of titanium oxide, a compound that is brilliant white in powder form on Earth but could behave in unexpected ways under such extreme conditions. The intense heat might also be breaking apart any molecules that could scatter light, leaving behind a haze of pure, light-hungry atoms. Or perhaps there are compounds in that atmosphere we have not even discovered yet, substances that thrive only in such alien ovens. This profound darkness forces us to rethink the very palette of the universe. How does a planet become a master of light absorption? What does this tell us about the hidden diversity of chemistry on worlds we have yet to find? TRES-2b stands as a shadowy monument to the fact that even the most basic property of an object, its color, can become a deep cosmic mystery when the rules of nature are pushed to their limits. That profound darkness gives way to a world of shocking, brilliant color. HD 189,733b appears from a distance as a serene, deep blue marble, a hue reminiscent of Earth's oceans as seen from space. But this beautiful azure tint is a cosmic deception, the signature of an atmosphere in a state of perpetual, violent chaos. This is a world where the sky rains molten glass. The planet is a gas giant orbiting so close to its parent star that its atmosphere is superheated to around 1,700 degrees Fahrenheit, hot enough to vaporize rock. Within this searing envelope, silicate particles, the basic building blocks of sand and glass on Earth, are not solid. They are vaporized into a gaseous form, rising high into the alien sky. As these silicate gases encounter slightly cooler layers of the atmosphere, they do not form clouds of dust or water vapor. Instead, they condense directly into microscopic droplets of liquid glass. This creates a permanent, global haze of silicate aerosols that scatter blue light, giving the planet its stunning and deadly azure glow. But the weather here is anything but serene. The planet is tidally locked with one scorching day side and one cooler night side, creating a titanic temperature difference that drives supersonic winds. These winds scream across the atmosphere at speeds exceeding 4,500 miles per hour, nearly 7 times the speed of sound. Imagine a sandstorm on our own world, a gritty, howling wall of dust. Now heat every single grain until it melts into a liquid droplet and accelerate the entire storm to velocities faster than a hypersonic jet. That is the reality on HD 189,733b. The sky is filled with a horizontal, scouring rain of molten glass, a tempest that would erode any surface to nothing in moments. Spectroscopic studies from telescopes like Hubble have confirmed the presence of these silicate particles, allowing us to peer directly into the chemistry of this alien storm. This forces us to confront the sheer diversity of planetary weather. We have water cycles on Earth, methane cycles on Titan, and now we must add silicate cycles to our celestial meteorology. What would it be like to witness such a storm, to see a blue sky that is not a promise of calm, but a warning of a coming, incandescent hurricane? More importantly, how do these hellish conditions reshape our search for habitable worlds? They serve as a critical reminder that a planet's color or position is no guarantee of its environment, that the universe crafts beauty from the most brutal and unforgiving processes. From a world sculpted by liquid stone, we journey to one that seems to defy the very logic of what a planet can be made of. The concept of a world forged from diamond is not just science fiction, but a startling scientific possibility. Orbiting a rapidly spinning stellar corpse known as a pulsar, over 4,000 light-years away, is a planet designated PSRJ 1719-1438b. This world is the probable remnant of a catastrophe, the surviving core of a once massive star that avoided complete destruction. The theory, supported by its incredible density and the unique environment of its pulsar parent, suggests this planet could be composed largely of crystallized carbon, a diamond on a planetary scale. To understand how such a glittering anomaly could form, we must revisit the life cycle of stars. A star much larger than our Sun eventually exhausts its nuclear fuel, leading to a catastrophic supernova explosion. In the furious fusion processes of that explosion, lighter elements are forged into heavier ones, including vast amounts of carbon and oxygen. If the star was originally rich in carbon, the violent expulsion of its outer layers can leave behind a core composed almost entirely of this element. This is the proposed origin story of PSRJ 1719-1438b. It is not a planet that formed from a dusty disk like Earth, but the salvaged heart of a dead star, now orbiting the ultra-dense neutron star that was its companion. The immense gravitational pressure from its own mass, combined with the searing heat of the supernova, would have compressed that carbon core into a crystalline structure. Planetary scientists note that its observed density is perfectly consistent with that of diamond, a form of carbon where atoms are locked into an incredibly strong and rigid lattice. We can think of it as the natural diamond formation process on Earth, but magnified to an almost incomprehensible degree. On our world, diamonds are created deep in the mantle where carbon is subjected to immense heat and pressure over millions of years. This alien world is in essence a single diamond that formed in an instant of cosmic violence, a gemstone the size of a planet. The challenges of directly observing such a distant object orbiting a faint pulsar mean its glittering composition remains a compelling theory, yet it forces profound questions about the nature of matter under extremes. What other exotic states of matter might exist on worlds forged in stellar furnaces? Could entire cosmic landscapes be built from materials we consider rare and precious? This revelation of a possible diamond planet expands our imagination of what constitutes a world, and it prepares us for solar systems where the orbits themselves are the source of profound mystery. A stable orbit in a sky filled with 3 suns should be an impossibility. Yet, against all odds, the gas giant HD 131,399 AB exists in exactly such a gravitational ballet. Located about 340 light-years away, this world orbits the brightest star in a triple star system, a configuration that should spell instant doom for any forming planet. The sheer gravitational chaos of multiple massive bodies pulling in different directions typically shreds protoplanetary disks or flings nascent worlds into the void. That this planet not only formed but maintains a stable, though extraordinarily wide, path is a profound anomaly that defies our models. Through the power of direct imaging with instruments like the Very Large Telescope, we have witnessed this world directly, a faint speck of light orbiting its primary star at a distance roughly twice that of Pluto from our Sun. The 2 other stars in the system orbit each other closely, and together they swing around the primary star in a wider dance. The planet's survival hinges on a delicate gravitational sweet spot. It remains bound to its primary star because that star's pull is dominant at such a great distance, while the gravitational tugs from the binary pair are too weak to disrupt its orbit. It is a cosmic balancing act of immense precision, akin to carefully placing a marble on a vast, undulating sheet that is being gently shaken at multiple points and having it stay perfectly in place. On the surface of such a world, the concept of a day or a year loses all earthly meaning. For long stretches of its 550 Earth-year orbit, all 3 suns would be visible in the sky, casting overlapping shadows and creating a perpetual, if variable, daylight. There would be times when the primary star sets, leaving the planet bathed in the dimmer, combined glow of the binary pair for a kind of eternal twilight. Then, as the orbital dance continues, there would come a period of true night when all 3 stars are below the horizon, a brief but profound darkness before the triple dawn returns. How would any form of life, or even basic geology, adapt to such an irregular and dramatic cycle of light and heat? The very existence of this planet forces astronomers to rewrite the rules for where we can look for worlds. It proves that planets can form and persist in the most gravitationally crowded neighborhoods of our galaxy, expanding the potential real estate for planetary systems far beyond single, quiet stars like our own. From a world that thrives in stellar chaos, we turn to a discovery that suggests some planets may not form around stars at all, drifting instead through the cold, eternal night between them. The stability of a triple star system is a marvel of cosmic order, but some planetary discoveries seem to exist solely to break our established rules. Orbiting a small, cool red dwarf star 600 light-years away is a world that should not exist. Designated NGTS 1b, this planet is a gas giant nearly the size of Jupiter, yet it circles a star that is only half the mass and radius of our Sun. This pairing is so improbable that astronomers have labeled it a forbidden planet, a direct challenge to everything we thought we knew about how solar systems are born. The prevailing theory, called core accretion, suggests planets form slowly from the bottom up. Dust grains in the disk around a young star clump together to form rocks, then planetary embryos, and finally, over millions of years, a solid core massive enough to pull in vast amounts of gas to become a giant like Jupiter. The problem is that small stars like red dwarfs have correspondingly small, lightweight protoplanetary disks. There simply should not have been enough raw material in the disk around NGTS-1 to build a planet of such staggering scale. It is like trying to build a mansion with only enough lumber for a garden shed. The numbers just do not add up. The discovery, made by the Next Generation Transit Survey, which scans for the faint dimming of starlight, sent a shockwave through planetary science. So how did this forbidden giant come to be? Experts propose several radical alternatives. One possibility is a process called disk instability, where a massive, cold region of the protoplanetary disk collapses directly under its own gravity, forming a gas giant in a cosmic blink, bypassing the slow core accretion model entirely. Another, perhaps more likely, scenario involves dramatic planetary migration. NGTS-1b may have formed much farther out in the disk, where more material was available, and then spiraled inward over time, settling into its current close orbit. Adding to the mystery is the star's surprisingly low metallicity, meaning it lacks heavy elements that are considered the building blocks for rocky planetary cores. This makes the core accretion model even harder to justify. Furthermore, the planet itself is puffed up, with an inflated radius likely due to the intense heat from its nearby star. The entire system feels like a paradox, a giant balloon tethered to a small pole by forces we are only beginning to comprehend. This single forbidden world forces a humbling admission that our models of planetary formation are incomplete. What other impossible pairings are waiting in the data, silently defying our textbooks? The existence of NGTS-1b opens the door to a universe where planet formation is far more diverse and dynamic than we ever dreamed, a necessary precursor to confronting a world where the climate itself has been pushed to a terrifying extreme. A planet where the sky rains liquid iron presents a climate so severe it seems impossible to surpass, yet the universe always finds a way to craft something stranger. On the ultra-hot Jupiter WASP 76b, the weather forecast calls for snow, but not the gentle, frozen water we know. Here, the precipitation is metallic, with flakes of iron, lead, and zinc potentially dusting the eternal night. This bizarre phenomenon is driven by the most extreme temperature contrast we have yet observed on an alien world. Like others in its class, WASP 76b is tidally locked, with one hemisphere perpetually facing its star. The dayside is a furnace, with temperatures soaring to over 4,000 degrees Fahrenheit, hot enough not just to melt iron, but to vaporize it, turning solid metal into a gaseous mist in the atmosphere. The night side, by contrast, plunges into a profound and permanent chill, hundreds of degrees cooler. This staggering difference does not create a gentle breeze. It fuels supersonic winds that scream from the day to the night, carrying the vaporized metals across the terminator line into the darkness. As these metallic vapors hit the cooler air of the night side, they do not simply linger. Spectroscopic observations from powerful telescopes have captured a telling signature. The chemical fingerprint of iron vapor is strong and clear in the dayside atmosphere, but it vanishes completely when scientists analyze the night side. The most logical explanation is condensation. The iron gas cools past its condensation point and turns directly into liquid droplets, which then fall as a rain of molten metal. As these droplets fall through even colder layers, they could solidify into fine, metallic snow. Researchers suggest other heavy elements like sodium, magnesium, and silicon could undergo the same dramatic phase change, creating a multi-mineral blizzard. The thermodynamics are familiar in principle, the same cycle that evaporates water from our oceans and deposits it as snow on mountain peaks. But here, the substances involved and the scale are utterly alien. Imagine the process inside an industrial foundry, where metal is heated until it flows like water and then poured into molds to solidify. Now envision that process happening across an entire planetary hemisphere, driven by the heat of a star and the planet's own furious winds. What would the landscape of such a world become over eons? Would metallic snow accumulate into shimmering, conductive mountain ranges? Could it form vast, solidified lakes of alloy? This metallic cycle forces us to radically expand our definition of a planetary weather system. We must now consider not just water or methane, but iron and silicate cycles as fundamental forces shaping alien worlds. It reveals a universe where the very air can be mined for resources, and where the most familiar processes are rendered in materials of astonishing value and danger. From a world slowly shedding its essence as metallic snow, we are pulled toward an even more ephemeral discovery, a planet that is not just changing, but actively dissolving into the void of space. The metallic snows of WASP 76b represent a world in a state of constant, violent transformation. But there is a planet where that change is so profound it is actively vanishing. GJ 436b is a world caught in the act of evaporation, leaving a ghostly trail of its own essence across the cosmos. This Neptune-sized exoplanet orbits a small, active red dwarf star so closely that its year is just over 2 Earth days. The star bombards the planet with an intense torrent of high-energy ultraviolet radiation, and that radiation is doing something extraordinary. It is literally boiling the planet's atmosphere away into space. This is not a gentle leak, it is a catastrophic loss. The process is called hydrodynamic escape, and it works like this. The ultraviolet light from the star carries immense energy. When it strikes the upper layers of the planet's hydrogen-rich atmosphere, it heats the gas to incredible temperatures, tens of thousands of degrees. This gives the hydrogen atoms so much kinetic energy, so much speed, that they overcome the planet's gravity entirely. They do not just rise, they achieve escape velocity and stream away into the void, like steam rushing from a boiling kettle with the lid removed. The Hubble Space Telescope provided the stunning evidence, using its keen eye in the ultraviolet spectrum to detect a giant, diffuse cloud of hydrogen enveloping the planet and stretching out behind it in its orbit. This cloud is not small, it forms a vast comet-like tail that is larger than the star itself, a visible monument to the planet's disintegration. To visualize the scale, think of a block of dry ice left on a table. You see the wispy, cold vapor streaming off its surface as it transitions directly from a solid to a gas. GJ 436b is undergoing a similar phase change, but instead of a block of frozen carbon dioxide, it is an entire planetary atmosphere, and instead of room temperature air providing the energy, it is the fury of a star. The implications are staggering. This process may have been commonplace in the early universe, especially around volatile red dwarf stars. It forces us to ask how many worlds like ancient Earth began with thick, hydrogen-rich envelopes only to have them stripped away by a young, violent sun. Our own planet's atmosphere is a secondary one, outgassed from the interior after the primordial hydrogen was likely lost to space. GJ 436b offers us a real-time window into that critical transitional phase, a snapshot of planetary evolution that is usually hidden in the deep past. Watching a planet evaporate reframes our search for life, highlighting the delicate balance between a star's warmth and its wrath. It also prepares us for a discovery where the very substance of a world becomes the central mystery, a planet whose impossible density seems to defy the laws of physics themselves. A world of pure iron would be dense beyond belief, but the universe has crafted a rocky planet that pushes the very concept of solidity to its limit. Kepler 10c, discovered in data from the Kepler Space Telescope, is a true cosmic heavyweight, a planet so massive it earned the nickname Mega-Earth. Its existence is a direct challenge to our understanding of how planets are built. We know rocky worlds like our own, and we know gas giants like Jupiter, but Kepler 10c defies that simple division. It has a mass 17 times that of Earth, yet its measured density tells us it is not a puffy, gaseous mini-Neptune. It is a solid, rocky behemoth. This means it has roughly the same density as our planet, but scaled up to a staggering size. For a world that large to remain rocky, its composition must be extraordinarily rich in heavy elements. Planetary scientists theorize its interior could be packed with metals like iron, or even rarer, denser elements such as osmium or platinum. The formation story of such a world is as compelling as its density. It likely originated in a protoplanetary disk that was exceptionally rich in solid material, a cosmic construction zone overflowing with the building blocks of rock and metal. In a more typical disk, a planet growing to this mass would have quickly gathered a massive envelope of hydrogen and helium, becoming a gas giant. But here, perhaps because the disk was depleted of light gases early on, or because it formed farther from its star where ices could add mass, the planet just kept accumulating solid material. Imagine the core of our own Earth, a sphere of mostly iron and nickel about the size of the Moon. Now envision an entire planet where that dense, metallic structure is not just the core, but makes up a significant portion of the whole world. The geological reality of Kepler 10c would be unimaginably intense. The pressure at its core would be millions of times greater than the pressure at the bottom of Earth's deepest ocean trench, creating states of matter we can only simulate in laboratories. Would there even be tectonic activity as we know it, or would the sheer weight of the planet lock its surface into a single, unbroken shell of super-compressed rock? What kind of mountains could form under such gravity, and how would the very concept of geology be rewritten? This mega-Earth forces us to ask fundamental questions about the limits of planetary science. Is there a maximum size for a rocky world, a point where gravity triggers a collapse or inevitable gas accumulation? Kepler 10c suggests the boundary is far larger than we ever presumed, revealing a hidden category of super-solid worlds in the cosmos. From a planet defined by its immense, compacted mass, we are drawn to one whose very motion in space presents a puzzle that seems to defy celestial mechanics. The orderly spin of a solar system is not a universal rule, but a cosmic suggestion that some worlds choose to ignore. Orbiting a star over 1,000 light-years away, the gas giant HDP-7b is a planetary rebel, moving in a direction opposite to the spin of its own sun. This is a retrograde orbit, a path so fundamentally backwards it challenges the very blueprint we use to explain how solar systems are born. The standard model, the nebula hypothesis, paints a serene picture. A cloud of gas and dust collapses, spinning faster as it shrinks, forming a star at the center and a flat, swirling disk of material around it. From this disk, planets coalesce, all inheriting the same direction of motion, like riders on a merry-go-round, all moving together. HTP 7b broke free from that carousel. Its orbit is not just retrograde, it is also highly tilted, nearly perpendicular to the star's equator. Radial velocity studies, which measure the star's subtle wobble, have confirmed this bizarre configuration. So how does a planet end up on such a rebellious path? The answer points to a violent and chaotic youth. In a young, crowded planetary system, gravitational interactions are not gentle nudges but titanic shoves. One leading theory is planet-planet scattering. Imagine several young gas giants forming in close proximity. Their gravitational pulls can destabilize each other's orbits, leading to a cosmic game of billiards. In a close encounter, one planet could be slingshotted inward on a wildly elliptical orbit, while another is ejected into the void. For HTP 7b, such an encounter may have flung it into a highly inclined, elongated orbit. Over time, the drag from the remaining protoplanetary disk and the tidal pull of the star could have circularized its path, but left it spinning backwards relative to its host. Another mechanism involves a distant companion, like a binary star or a massive planet farther out. Through a process called quasi-oscillations, the gravitational tug from this distant object can slowly torque and flip the inner planet's orbit over millions of years, turning its motion upside down. This discovery forces a profound reassessment of planetary system evolution. Our own solar system, with its planets marching in orderly, prograde orbits, may be the exception rather than the rule. It suggests that many young systems undergo periods of extreme gravitational turmoil, a phase of planetary realignment that can leave lasting scars on a world's trajectory. What does this mean for the potential stability of Earth-like worlds in such systems? Could a habitable planet survive these gravitational upheavals, or are they relegated to quieter, more isolated stars? HTP 7b stands as a testament to the dynamic, often violent processes that sculpt planetary families, reminding us that a planet's present path is often a record of a tumultuous past. From a world that defies orbital convention, we are drawn to one that seems to defy the very flow of time itself, a planet where a year passes in less than a single Earth day. A polar orbit transforms a planet's journey from a simple circle into a dramatic high-latitude crossing. EXO 3b is a massive gas giant that does not travel around its star's equator like the planets in our solar system. Instead, its path is steeply inclined, carrying it over the star's polar regions in a looping, celestial meridian. This rare configuration was detected not by seeing the planet directly, but by measuring a subtle distortion in the starlight itself, an observational trick known as the Rossiter-McLaughlin effect. As the planet transits or passes in front of its star, it blocks a portion of the rotating star's light. Because one side of the star is spinning toward us and the other away, the planet blocks light from different, moving parts of the stellar surface, creating a telltale wiggle in the star's spectral signature. This wiggle revealed the planet's bizarre, pole-spanning trajectory. Such a dramatic orbital tilt does not happen by accident. It is a gravitational scar, a lasting sign of a turbulent past. Astronomers theorize that a distant, massive companion, perhaps a second star or a giant planet in a wide orbit, exerted a persistent gravitational tug on EXO 3b over eons. This distant perturber slowly torqued the planet's orbit, pulling it upward and out of the equatorial plane until it settled into this stable but highly inclined path. It is a process of gravitational sculpting where the silent influence of an unseen object can completely redefine a world's relationship with its sun. The climatic consequences of a polar orbit are profound. Unlike Earth, whose tilted axis gives us seasons as we orbit, A planet in a polar orbit experiences seasons based on the changing angle of its entire path. Imagine a world where for half of its year, one pole is constantly aimed at the star, baking under perpetual daylight, while the opposite pole endures an endless, frigid night. Then, as the orbit progresses, the roles reverse. The star's illumination sweeps from pole to pole, creating global seasonal shifts of unimaginable intensity. There are no temperate latitudes offering refuge, just a slow, grinding exchange between two extremes of heat and cold. Over even longer timescales, the orbit itself can precess or wobble, like a spinning top slowing down, causing these seasonal patterns to drift over millennia. What does this mean for the possibility of life? A polar orbit introduces a level of climatic instability that would challenge even the hardiest organisms. The constant, drastic redistribution of stellar energy could prevent the establishment of any stable climate zones, making the long-term chemical processes necessary for life as we know it extraordinarily difficult. Yet, this very instability provides crucial clues. Finding a planet like XO3b is like discovering a fossilized footprint next to a strange rock. It tells us that something massive passed by long ago. Its polar orbit is direct evidence of gravitational interactions that reshaped its solar system, offering astronomers a forensic tool to reconstruct historical events they could never witness. It proves that planetary systems are not static arrangements but dynamic sculptures, continually molded by invisible forces. This search for missing gravitational actors leads us to a different kind of absence, a planet that seems to be missing something fundamental from its very atmosphere. The clarity of a planetary atmosphere can be as revealing as its most violent storms. WASP 96b presents us with a sky of startling transparency, a cloudless blue world that offers an unobstructed view into the heart of a distant gas giant. This hot Jupiter, orbiting a star over 1,000 light-years away, should by all accounts be shrouded. Planets in its temperature class, with atmospheres heated to over 1,000 degrees Fahrenheit, are typically expected to be blanketed by thick clouds of silicate or salt particles, much like the permanent haze on HD 189,733b. Yet when astronomers pointed powerful telescopes like the Very Large Telescope toward WASP 96b as it passed in front of its star, they saw something extraordinary. The starlight filtering through the planet's atmosphere carried a pristine and unmistakable signature, the complete spectral fingerprint of sodium, with none of the telltale flattening or muting that clouds would cause. It was as if they were looking through a perfectly clean window into the planet's gaseous layers. This detection, a triumph of transmission spectroscopy, was remarkably clean, also showing a notable absence of potassium, further supporting the conclusion that the atmosphere is free of the obscuring condensates that form clouds. The method itself is elegant. Scientists capture the spectrum of starlight twice, once when the planet is beside its star, and once during the transit when the planet's atmosphere acts as a filter. The difference between these two spectra reveals the chemical makeup of the air itself, atom by atom, molecule by molecule. For WASP 96b, that chemical story is one of surprising simplicity and clarity. So why is this world so clear when others are shrouded? The answer lies in a delicate balance of atmospheric chemistry, temperature, and composition, what scientists term metallicity. At the scorching temperatures on WASP 96b, the compounds that might form cloud seeds like silicates or titanium oxide may remain entirely in gaseous form, never cooling enough to condense. Alternatively, the planet's atmosphere might have a lower abundance of these cloud-forming elements to begin with, a lower metallicity, meaning there simply isn't enough raw material to build a global overcast. Imagine the difference between a humid summer day where water vapor readily condenses into thick, billowing cumulus clouds and a crisp, dry desert day where the sky is a deep, cloudless azure from horizon to horizon. WASP 96b represents that eternal desert clarity on a planetary scale. This transparency is a gift for planetary scientists, providing a cleaner, less ambiguous signal to decode. It allows for more precise measurements of atmospheric composition, pressure, and even wind patterns, building a clearer model of the planet as a whole. Yet it also poses a profound puzzle, forcing us to ask why atmospheric recipes vary so dramatically from one hot Jupiter to the next. What subtle differences in formation history or subsequent stellar irradiation determine whether a world will be veiled or unveiled? This clear window stands in stark contrast to our next destination, a world so utterly shrouded that its very surface remains a conjecture hidden beneath an atmosphere of crushing mystery. The pristine clarity of a cloudless sky gives way to a world of impossible lightness. HETP-1b is a cosmic hot air balloon, a gas giant so profoundly inflated it defies the standard relationship between size and mass. This puffy planet, orbiting one component of a binary star system, has a radius significantly larger than Jupiter's, yet it possesses barely half the mass. Its density is so astonishingly low it would float on water if we could find an ocean large enough to hold it. This is not a simple matter of a large planet. It is a structural anomaly where the very fabric of the world seems stretched to its limit, challenging our fundamental equations of planetary structure that balance gravity's inward crush against internal pressure's outward push. So what mysterious force is keeping this world perpetually bloated? The leading theory points to an extraordinary internal heat source. While all gas giants retain some primordial warmth from their formation, HETP-1b seems to harbor an excess. One possibility is intense tidal heating. If its orbit is not perfectly circular, the varying gravitational pull from its star could flex the planet's interior, generating friction and heat much like repeatedly bending a metal coat hanger warms it up. Another compelling idea involves the star's intense radiation. The planet orbits exceptionally close to its host, bathing its atmosphere in a torrent of energy. This stellar input might be trapped by high-altitude atmospheric compounds with significant opacity, acting like a thick blanket that prevents heat from escaping, causing the entire outer envelope to swell. Some researchers even speculate about the influence of a strong internal magnetic field, which could channel energy into the upper atmosphere, contributing to the expansion. To visualize this, picture a loaf of bread baking in an oven. The dough's mass does not increase, but the heat causes gases within it to expand, making the loaf rise into a light, airy structure. HETP-1b is a planetary-scale version of that process, its atmosphere kept perpetually risen by an internal oven we are still working to understand. This profound puffiness raises urgent questions about the life cycle of such worlds. What is their ultimate fate? Without a constant source of that extra internal energy, the atmosphere could slowly contract under its own gravity. More dramatically, if the heating is too intense, it might drive the upper layers to expand beyond the point of gravitational binding, leading to a gradual but catastrophic loss of atmosphere into space, similar to the evaporation of GJ 436b, but driven from within. HETP-1b represents a delicate and transient state in planetary evolution, a reminder that worlds are not static sculptures but dynamic systems in constant negotiation between internal forces and external bombardment. This delicate balance of inflation and potential loss finds a stark counterpart in a world whose entire existence is defined by a wildly lopsided and unpredictable path. The delicate balance of a puffy planet is a whisper compared to the violent whiplash orbit of HD 80606b. This world does not travel in a neat circle or even a gentle ellipse. It follows a path of breathtaking eccentricity, a cosmic roller coaster that takes it from a blistering close approach to a frigid, distant swing within a matter of Earth months. Its orbit is one of the most extreme ever measured, a stretched oval that defies the typical, placid paths of planets in our own solar system. The journey begins at a pastron, the orbit's farthest point, where the planet is a frozen wanderer over 80 million miles from its star, a distance comparable to Venus's orbit in our system. Here, the Sun would appear as little more than a bright star in a perpetual night sky, and temperatures plummet to hundreds of degrees below zero. Then, gravity's inexorable pull takes over. The planet begins its long fall inward, accelerating to phenomenal speeds as it races toward its star. At Periastron, the closest point, it screams past its Sun at a distance of less than 3 million miles, closer than Mercury is to our Sun, in a searing flyby that lasts only a few harrowing days. During this close encounter, the side facing the star is flash-heated from a deep freeze to an inferno exceeding 2,000 degrees Fahrenheit in a matter of hours. The star would swell in the sky from a point to a terrifying, blazing disk dozens of times larger than our Sun appears, unleashing a torrent of radiation. Then, just as quickly, it recedes, cooling rapidly as it climbs back toward the frozen depths of its orbit. This dramatic cycle repeats every 111 Earth days. The origin of such a wild path is a gravitational scar from the system's youth. HD 80606b orbits one star in a binary pair, and astronomers believe the persistent tug of the companion star over eons has pumped up the planet's orbital eccentricity through a process known as the Kozai mechanism. It is as if the distant companion star gives the planet a persistent, rhythmic push at just the right point in its orbit, stretching its path further with each celestial nudge. Data from radial velocity curves, which chart the star's telltale wobble, graphically illustrate this drama, showing the star being pulled at dramatically different speeds as the massive planet swings close and then far away. The effects on the world itself must be cataclysmic. Theoretical models suggest the intense, rapid heating at Periastron likely triggers global shockwaves in the atmosphere, supersonic storms that redistribute the sudden influx of energy across the entire planet in a matter of days. The very rocks on any hypothetical surface would expand and contract with violent force, potentially leading to world-shattering seismic events. This creates a seasonal cycle unlike any other, driven not by a tilted axis but by the brutal geometry of the orbit itself. How could any form of stability emerge in such an environment? The concept of life adapting to these erratic conditions stretches the imagination beyond breaking, requiring resilience to changes more drastic than any ice age or warming period on Earth compressed into a single season. This world is a laboratory for the most extreme orbital dynamics, teaching us that planetary orbits are not always destined to circularize and calm. Some worlds bear the permanent mark of their system's chaotic gravitational history, forever traveling on a path of violent extremes. From a world defined by the shape of its wild journey, we are drawn to a planet whose very substance presents a different kind of mystery. A globe that might hold not rock or gas, but a single, endless global ocean. A world of endless ocean exists not in science fiction, but in the scientific data for a planet named GJ 1214b. This super-Earth, orbiting a dim red dwarf star 48 light-years away, presents a profound puzzle of composition. Its measured mass and radius give it a surprisingly low density, a value that sits perfectly between that of a rocky world like ours and a gaseous mini-Neptune. This single data point opens a door to two radically different realities, and astronomers cannot yet say for certain which one is true. The first and most captivating possibility is that GJ 1214b is a true water world. In this model, the planet would consist of a rocky, metallic core surrounded by a staggering volume of water, hundreds of kilometers deep, amounting to a significant fraction of its entire mass. The surface would not be a collection of continents and islands, but a single, global ocean under a thick, crushing atmosphere of steam. The second possibility is that it is a more conventional, though still exotic, mini-Neptune with a small rocky core enveloped by an immense, puffy atmosphere rich in hydrogen and helium. Our current tools struggle to definitively choose between these fates. Transmission spectroscopy, which analyzes starlight filtering through a planet's atmosphere, has so far revealed only a featureless, flat spectrum for GJ 1214b. This suggests a high-altitude layer of clouds or haze, perhaps composed of salt or photochemical smog, that is blocking our view of the deeper atmospheric layers where water's chemical signature might be hiding. It is like trying to identify the contents of a pot by looking at the lid. We know something is inside, but the steam is too thick to see through. The water world scenario, if true, tells a fascinating formation story. Such a planet likely formed far beyond the snow line of its system, where water exists as abundant ice, and then migrated inward to its current close orbit. The structure of this aquatic globe would be unlike anything in our solar system. At the very bottom, the immense pressure from the weight of the ocean above would compress the water into exotic, high-pressure forms of ice, not cold ice from a freezer, but hot ice forged under crushing force. This layer, called Ice 7 or superionic ice, would form a solid mantle above the rocky core, with a global, liquid ocean churning above it. We see a hint of this architecture on Jupiter's moon Europa, with its subsurface ocean locked under a shell of ice, but here the scale is planetary, and the ocean is the planet. The potential for chemistry in such an environment is staggering. With a rocky seabed in contact with a vast, warm, mineral-rich ocean under a thick atmosphere, many of the ingredients and conditions thought necessary for life's emergence could be present. Yet the challenges are equally immense: the crushing pressures, the potential for a runaway greenhouse effect turning the entire ocean to steam, and the violent flares from its red dwarf sun. Could life find a way in a perpetual, global sea? The very possibility forces us to expand our definition of a habitable zone to include worlds that are not Earth twins, but aquatic spheres holding more liquid water than exists on our entire planet. This profound mystery of hidden oceans leads us to a different kind of planetary force, one that is invisible yet shapes the very fate of a world, a magnetic field generated in a way that should be impossible. The deep oceans of a water world conceal a different kind of planetary shield, one that is invisible yet vital. HAT P11b, a Neptune-sized world 123 light-years away, presents a compelling mystery. It appears to generate a magnetic field far stronger than our models predict. This discovery did not come from seeing the field directly, but from observing its protective effects. Astronomers using the Hubble Space Telescope detected a giant, extended cloud of hydrogen evaporating from the planet. But with a peculiar twist, the cloud was not streaming away in a smooth tail as seen on other evaporating worlds. Instead, it was structured, clumpy, and seemed to be corralled, as if an invisible force was shaping its escape. The most likely explanation for this containment is a powerful planetary magnetosphere, a magnetic bubble generated deep within the world that pushes against the onslaught of its star's stellar wind. This is a revelation because generating a magnetic field in an ice giant like HT-P11b is a process far less understood than in rocky planets like Earth or gas giants like Jupiter. On Earth, our magnetic field is born from the churning of molten iron in the outer core, a geodynamo. Jupiter's immense field comes from the motion of conductive metallic hydrogen deep in its interior. But for a Neptune-sized world, which lacks both a large molten iron core and the pressures needed for metallic hydrogen, the source of the dynamo is more enigmatic. Experts studying atmospheric escape suggest the field likely arises from a different conductive layer, perhaps a vast, deep ocean of ionized water, superionic ice, or a salty ammonia solution under immense heat and pressure. The motion of this electrically conductive fluid, stirred by the planet's rotation and internal heat, could generate the surprising magnetic field we infer. We can think of it like a colossal version of a simple electric generator, where the motion of a conductor through a magnetic field creates an electric current, but here the entire planet is the machine, and the conductor is a global, sloshing sea. Detecting such fields directly is a frontier of science, often relying on hunting for faint radio emissions generated by the interaction between the stellar wind and the planetary magnetic field, a method that has proven successful for Jupiter in our own system. The implications of a strong magnetosphere are profound for a world's long-term fate. This magnetic shield can deflect the erosive stellar wind, dramatically slowing the evaporation of the atmosphere and potentially preserving it for billions of years. On such a planet, auroras would not be confined to poles as on Earth, but could ignite across the entire sky, a constant, shimmering curtain of light powered by the endless rain of charged particles from its star. This forces us to ask how crucial is a magnetic field for sustaining an atmosphere, and by extension, any potential for habitability. What can the magnetic personalities of distant exoplanets teach us about the history and future of Earth's own protective shield? The hidden dynamo of HETP 11b reveals that planetary protection comes in many forms, and sometimes the most powerful force is the one we can never see, a silent guardian sculpted from a world's deepest, darkest seas. This invisible force field stands in stark contrast to a planet whose most visible feature, its atmosphere, is not just changing, but appears to be vanishing and reappearing in a cycle we are only beginning to decipher. A planet's atmosphere should be a stable, defining feature, not a shifting illusion. GJ 3470b is a cosmic chameleon, a Neptune-sized world whose atmospheric signature seems to transform from one observation to the next, leaving astronomers to question what they are truly seeing. This anomaly strikes at the very heart of our ability to characterize distant worlds, revealing the profound challenges and limitations of even our most powerful telescopes. In some studies, the starlight filtering through this planet's air carries the clear spectral fingerprint of water vapor. In others, that same signature is conspicuously absent, replaced by a featureless haze or signs of entirely different molecules. The planet itself has not changed, but our window into its nature is frustratingly narrow and transient. Experts note that these discrepancies are not necessarily errors, but clues. They point to the immense difficulty of the task, where a single observation is a brief snapshot of a complex, dynamic system light years away. Factors like the intense and variable activity of the host star, the precise timing of the observation within the planet's orbit or its own weather cycle, and even the specific wavelengths of light used in the analysis can all paint dramatically different portraits of the same world. Stellar flares from the active red dwarf can bombard the atmosphere, triggering bursts of photochemistry that temporarily alter its composition, creating a smoky haze that obscures our view. To understand this, picture a world with weather patterns of staggering variability. One week, a global storm system of reflective clouds might blanket the planet, hiding the water-rich layers below. The next, a period of clearing could reveal the deeper, vapor-filled atmosphere, our telescopes taking a mere handful of hours of data during a transit that occurs every few days, might catch it in either state, each telling a different but equally true story. This forces a humbling realization that a single measurement is not a definitive biography, but a single page torn from a constantly rewriting book. Achieving consistent readings requires something we are only beginning to master: multi-wavelength campaigns that observe the same planet simultaneously with different instruments, building a composite, three-dimensional view of its atmosphere over time. The implications for climate stability on such worlds are profound. If an atmosphere can change its fundamental observable character so readily, what does that mean for the long-term equilibrium of temperature and pressure? Could a world oscillate between states that are, from our distant vantage point, unrecognizable from one century to the next? This chameleon world teaches us that planets are not static portraits but dynamic films, and we are only seeing isolated frames. It is a lesson in cosmic humility that prepares us for an even more extreme environment, a planet that does not orbit a living sun, but a dead one, enduring in the aftermath of stellar catastrophe. The fate of a planet is often sealed by the death of its star, but some worlds defy even that finality. Orbiting the dense, Earth-sized cinder of a white dwarf star 400 light-years away, the rocky body known as WD 1145 plus 017b offers a ghostly glimpse into a solar system's afterlife. This is not a planet in any traditional sense, but a disintegrating remnant, a testament to the violence of stellar death and the astonishing resilience of planetary material. The white dwarf itself is the final stage for a star like our Sun, the exposed, ultra-dense core left behind after it has shed its outer layers in a beautiful but destructive planetary nebula. During that earlier red giant phase, the star would have swollen to engulf and vaporize any inner worlds, a fate that likely awaits Mercury, Venus, and possibly Earth in our own distant future. Yet here, evidence suggests that some planetary bodies, perhaps from the outer system, survived that infernal expansion and migrated inward after the star's calm white dwarf phase began. The doomed object we detect is caught in an orbit so close that the white dwarf's fierce gravity is tearing it apart, a process called tidal disruption. Observations from telescopes like Kepler captured the star's light dipping in erratic, jagged patterns, not the clean, symmetric dip of a whole planet transiting, but the telltale signature of clouds of rocky debris streaming from a crumbling body. Spectroscopy of the white dwarf's atmosphere adds to the story, revealing it is polluted with heavy elements like iron, magnesium, and silicon, elements that should have sunk into the star's core eons ago. The only logical source is this ongoing rain of planetary debris, the final dust of a world being ground into atoms. It is a system reborn from its own ashes, a phoenix not of fire, but of dust and gravity. This forces us to confront profound questions about time and endurance. Could any world, perhaps one with a deep ocean or a thick, insulating crust, survive the red giant phase to become habitable again in the quiet, billion-year glow of a white dwarf? While the stable orbit would be close and the light dim, such a scenario is not entirely ruled out, offering a potential haven for life trillions of years into the universe's future. More immediately, WD 1145 plus 017b serves as a stark prophecy. It shows us the likely fate of our own inner solar system, a future where the Sun becomes a red giant and then a white dwarf, perhaps with the shattered remnants of asteroids or even a dismantled Mars spiraling in a final, dusty dance. From the solemn aftermath of a star's death, we shift our gaze to a spectacle of breathtaking scale and light, a ringed world that makes even majestic Saturn seem modest by comparison. Saturn's magnificent rings are dwarfed by a structure of almost unimaginable scale. Orbiting a young, sun-like star over 400 light-years away, the object known as J1407b is encircled by a ring system that makes our solar system's crown jewel appear miniature. This super Saturn, which may be a giant planet or a small failed star called a brown dwarf, is home to rings that stretch for tens of millions of kilometers, a disk of material roughly 200 times wider than Saturn's entire ring system. We did not see this colossal structure directly, but instead detected its breathtaking silhouette through a series of bizarre and prolonged eclipses of its parent star. Over a period of 56 days in 2007, the star's light dimmed in a complex, jagged pattern, not the clean, symmetrical dip of a planet, but a series of deep, irregular troughs and spikes. Astronomers analyzing this extraordinary light curve realized they were witnessing the shadows of an immense, finely detailed ring system passing in front of the star, a celestial vinyl record casting its grooves onto a stellar spotlight. The data suggests the rings are not a smooth sheet, but are divided into distinct bands separated by sharp, clean gaps. These gaps are the telltale signature of exomoons or shepherd moons, whose gravity carves out lanes in the ring material, just as Saturn's moon pan clears the Encke gap in its own rings. The scale, however, is almost incomprehensible. The entire gap structure implies a system of multiple moons, some potentially as large as Mars or Earth, acting as cosmic landscapers on an epic scale. The formation of such a vast ring system is a profound mystery. It could be the remnant of a protoplanetary disk that never coalesced into moons, frozen in time by the object's weak gravity if it is a brown dwarf. Alternatively, it might be the result of a cataclysmic event, like the tidal disruption of a massive moon or a planetary collision, whose debris was captured into orbit. The composition of the rings is another puzzle, likely a mix of dark, rocky dust and icy particles, constantly colliding and reshaping under the complex gravitational dance of the host and its shepherd moons. Directly imaging this system is currently beyond our reach, as the object and its star are too close together in the sky for our telescopes to separate. But we can imagine the view from a hypothetical moon within that system. The night sky would be dominated by a colossal, bright arc of rings stretching from horizon to horizon, their dusty surface reflecting the faint light of the distant star, segmented by dark bands where moons patrol their orbits. How long can such a magnificent, delicate structure last? Without constant shepherding, the rings would likely dissipate over millions of years, either collapsing into new moons or drifting away into space. Their very existence forces us to ask if our own Saturn, with its relatively modest rings, is the norm or the exception. Are gargantuan ring systems like this a common, fleeting phase in the life of giant planets, or a rare trophy of specific cosmic conditions? This majestic, ringed anomaly shows that even the most iconic features of our solar system can be rendered in scales that defy belief, orbiting a star that is, for now, keeping its greatest spectacle in shadow. The line between a planet and a star is not always a bright one. Orbiting a dim, cool object known as a brown dwarf, the companion in the System 2 mass J044144 presents a profound classification crisis. This pair, discovered through sensitive infrared imaging, consists of a brown dwarf and a smaller, planet-sized object locked in a gravitational embrace, each a mere few million years old. A brown dwarf is a cosmic in-between, often called a failed star. It forms like a star from the collapse of a gas cloud, but it never gathers enough mass to ignite the sustained hydrogen fusion that powers true stars like our Sun. Its core may flicker with brief deuterium fusion, but it primarily just glows with the residual heat of its formation, slowly cooling over billions of years into planetary temperatures. The mystery of 2 mass J044144 is not just what it is, but how it came to be. Did the smaller companion form like a planet, coalescing from a disk of dust and gas that swirled around the young brown dwarf? Or did both objects form simultaneously like a binary star system through the direct fragmentation of the same collapsing cloud? Our current observations cannot yet definitively answer this, making the system a living test of two competing theories of birth. The planet-like object, with a mass estimated at around 5 to 10 times that of Jupiter, sits right on the fuzzy boundary we use to separate giant planets from the smallest brown dwarfs. This gray area is sometimes called the brown dwarf desert, a rarity of such close-orbiting substellar companions that highlights the unusual nature of this pairing. To visualize the system, think of a fading ember from a campfire, still radiating a deep, ruddy heat. Orbiting it is a second, even dimmer coal, both born from the same flame but now destined to cool together in the cosmic dark. The temperatures here are far cooler than any star, perhaps just a few hundred degrees above absolute zero, with luminosities so faint they are invisible to the human eye. What does this mean for our definitions? If a planet can form around an object that is not a proper star, does that change what we consider a solar system? Furthermore, if the pair formed like twin stars, then the smaller object is not a planet at all, but a junior brown dwarf, making this a binary system of failed stars. This single, dim duo forces astronomy to confront the limitations of our categories. It reveals a continuum of objects from the most massive planets to the smallest stars, where formation history, not just mass or orbit, becomes the key to understanding their true nature. This blurring of celestial identities leads us to a planet where time itself is compressed into a frantic, dizzying rhythm, completing an entire year in less time than it takes our world to spin once on its axis. A world where an entire year passes in less time than a single Earth day is not a thought experiment, but a measured reality. Among the most extreme examples are planets like Kepler 78b, a scorched, Earth-sized world that completes its orbit in a mere 8.5 hours, and candidates like Swift-J 1756, 9-2508b, which may orbit a pulsar in just 20 minutes. These are the ultra-short period planets, celestial bodies moving at a blistering pace that places them impossibly close to the surfaces of their stars. To be in such a tight orbit means enduring an environment of almost inconceivable violence. The star's gravity is immense, creating tidal forces that would rip a less dense world apart. The radiation flooding the planet is thousands of times more intense than what Earth receives, a constant, sterilizing deluge of X-rays and ultraviolet light. That these worlds exist at all is a triumph of durability over physics. Their detection often relies on incredibly precise timing. For planets around pulsars, astronomers measure the minuscule, rhythmic variations in the arrival time of the pulsar's clock like radio pulses, deviations caused by the planet's gentle gravitational tug. Around normal stars, missions like Kepler spotted the faint, repeated dimming as these tiny worlds transit their suns in a frantic, hours-long cycle. The composition of such a survivor is almost certainly rocky and metallic, a dense cinder forged in stellar fire. Any gaseous envelope would have been stripped away eons ago by the stellar wind. The surface itself is likely a global ocean of molten rock, a permanent magma ocean churned by the star's fierce gravity. Such a planet would also be tidally locked, with one hemisphere facing the eternal stellar furnace and the other locked in darkness, though the difference might be negligible given the searing heat radiating across the entire globe. This proximity places the planet in a precarious dance with destruction. It orbits so close that it likely skims the outer fringes of the star's corona, its atmosphere, if any remains, continuously ablated by the stellar wind. More critically, the orbit itself is unstable. The same tidal forces that lock the planet also cause orbital decay, a slow but inevitable spiral inward as energy is dissipated. The planet is orbiting inside what is known as the Roche limit, the distance where a star's gravity overcomes a world's own self-gravity. While a solid, rocky body can hold itself together for a time, the relentless drag will eventually win, pulling the planet into a final, catastrophic merger with its star. To grasp the timescale of its existence, imagine watching a feature-length film. From opening credits to final scene, an entire year could pass on such a world multiple times over, each orbit a fleeting sprint from one sunrise to the next, if a sunrise could even be perceived in the permanent glare. This forces two profound questions. First, how did the planet get there? It almost certainly could not have formed in place, as the primordial protoplanetary disk would have been too hot for dust to coalesce so close to the newborn star. The leading theory is dramatic migration, a journey from the cooler outer system driven by gravitational interactions, a journey that ended in this searing, final parking orbit. Second, what is the absolute lower limit for an orbital period? Is a 20-minute orbit the edge of possibility, or could something even closer, something lasting mere seconds, exist for a brief moment before being consumed? These ultra-short period worlds are the final, desperate laps in a cosmic race against time, showing us the ultimate extremes of where a planet can, however briefly, exist. This frantic pace finds a strange echo in a system where two worlds share not just a star, but the same precise celestial pathway, moving in an impossible, synchronized lockstep. Two suns are not just science fiction, but a proven reality in our galaxy. Kepler 16b is a world of profound dual allegiance, a Saturn-sized gas giant that orbits not one, but two stars locked in a tight gravitational embrace. This circumbinary planet, the first of its kind confirmed by the Kepler Space Telescope, validates the iconic twin sunset of Tatooine as a genuine cosmic phenomenon. Its discovery was a masterclass in celestial deduction, relying on the clockwork precision of stellar eclipses. The two stars, one about 2/3 the mass of our Sun and the other a fifth, regularly pass in front of each other from our vantage point, causing predictable dips in brightness. Yet astronomers analyzing the Kepler data noticed additional, smaller dimmings that occurred at irregular intervals, but always when both stars were fully visible. This precise timing revealed a third body, a planet whose orbit around both stars occasionally lined up to block their light. The very existence of a stable orbit here is a triumph over gravitational chaos. Binary stars whip around each other quickly, in this case every 41 days, creating a shifting center of mass. For a planet to survive, it must orbit far enough outside this turbulent inner zone to avoid being flung into the void, a delicate solution to the infamous three-body problem. Kepler 16b maintains a wide, cautious path, completing a year in about 229 Earth days. The climate on such a world would be dictated by a complex ballet of light. The two stars, one orange and one red, would chase each other across the sky in a mesmerizing dance. There would be single sunrises, double sunrises, and eclipses where one star passes in front of the other, casting a sudden, deep shadow across the landscape. The combined light and heat create a habitable zone, but it is a region that moves and warps with the star's orbital dance, making the concept of a stable, temperate band far more dynamic. How could a planet even form in such an environment? The leading theory suggests it coalesced in a protoplanetary disk that encircled the entire binary system, a feat once thought improbable due to the disruptive gravitational tides. Its success proves that planets can assemble in the most crowded stellar neighborhoods. This forces us to ask, could a rocky world exist in the habitable zone of a binary system? The potential for seasons driven by two light sources, with periods of amplified warmth and others of compounded chill, adds layers of complexity to the idea of alien climates. Yet the very stability of Kepler 16b offers hope that such worlds could provide enough environmental consistency for chemistry, and perhaps even biology, to take hold. From a world bound to two suns, we are drawn to the opposite extreme, a planet with no sun at all, wandering the eternal night between stars. The freedom of a rogue planet is a profound cosmic solitude, but some worlds may find a home after a lifetime of wandering. HD 106906b is a gravitational enigma, a massive world orbiting its star at a staggering distance of over 650 times the span between Earth and our Sun. At such a separation, this planet exists in a realm of perpetual twilight, where its sun appears as little more than the brightest star in a dark sky, and a single orbit takes 15,000 Earth years to complete. This vast gulf is not the only oddity. Its orbit is also dramatically tilted and misaligned with the rest of the system's dusty debris disk, as if it were placed there by an unseen hand. Discovered through the power of direct imaging with instruments like the Gemini Planet Imager and the Hubble Space Telescope, this object is young, hot from its recent formation, and massive, estimated at about 11 times the mass of Jupiter. This places it squarely on the blurred boundary between a superplanet and a small brown dwarf, a failed star. The central mystery is its origin story. How did such a massive object end up in such a wide, misaligned orbit? There are two compelling and radically different possibilities. The first is that it formed in place, coalescing from the outer reaches of the protoplanetary disk just like any other planet. The second, and far more captivating theory, is that HD 106906b began its life as a rogue planet, a free-floating world ejected from its own birth system, only to be later captured by the gravity of this foreign star as it drifted by. This capture scenario would explain the peculiar orbit perfectly. A gravitational encounter in a young, dense star cluster could have flung the planet inward from the system's outskirts, or even captured it from the interstellar void entirely. The process is akin to a cosmic game of gravitational pinball, where a passing object is snared by a star's gravity and settles into a stable, if eccentric, new path. The challenges of detecting such a distant companion are immense, requiring instruments capable of blocking the star's overwhelming glare to see the faint, warm glow of the planet itself. This potential captured rogue forces us to reconsider the very mobility of planets. How many orphaned worlds drift unseen in the darkness between stars? Billions, according to some estimates, and if a rogue planet like this can be captured, could it bring with it a retinue of moons? Such a moon, warmed by tidal forces from the giant planet rather than a distant sun, could theoretically maintain a subsurface ocean for billions of years, a hidden oasis in a system it was never born into. This wandering mystery of celestial adoption brings us to a planet whose most defining feature is not its orbit, but the magnificent, evaporating tail it leaves in its wake. The dusty remains of a world can become its most visible feature. KIC 12,557,548b is a ghost in the data, a rocky world that is less a solid sphere and more a disintegrating cloud, trailing its own essence behind it like a comet's mournful tail. This candidate planet, discovered in the meticulous observations of the Kepler Space Telescope, presents one of the most ephemeral and haunting anomalies in our catalogue. Its transit signal is unlike any other, not a clean, U-shaped dip in starlight, but an asymmetric, variable dimming that changes shape and depth from one orbit to the next. Astronomers analyzing this bizarre signature concluded they were not seeing a planet's silhouette at all, but the shadow of a vast, dynamic cloud of dust and debris streaming away from a tiny, scorched core. This cloud stretches far into space, blown backward by the pressure of the star's radiation, creating a tail that makes the entire object appear hundreds of times larger than the rocky body at its heart. The planet itself is incredibly close to its small, active star, completing an orbit in less than 16 hours. At such proximity, the dayside temperature is estimated to approach 3,000 degrees Fahrenheit, hot enough to vaporize rock. The leading theory for this dramatic disintegration is a process called sublimation, where the surface rock turns directly from a solid into a gas under the intense stellar heat. This vapor then condenses into microscopic dust grains as it rises and cools in the upper atmosphere. The star's fierce radiation and stellar wind then blow this fine dust away, but the planet's gravity is too weak to hold it, creating a perpetual, accelerating loss. Another mechanism could be electrostatic lofting, where intense electrical charges on the hot, dry surface literally levitate dust particles into the thin atmosphere, where the stellar breeze carries them off. To visualize this, think of a dry, dusty road on a hot, windy day. Gusts lift the fine silt into a hazy cloud that drifts downwind, obscuring the road itself. Now imagine that road is an entire planet. The wind is the light of a star, and the process never stops year after year, millennium after millennium. The dust cloud is not static, its density and size fluctuate, which explains why the transit depth varies so dramatically. Some passes barely dim the star, suggesting a thin veil of dust, while others create a much deeper shadow, indicating a dense, opaque shroud has formed. Scientists modeling the phenomenon estimate the dust grains are incredibly fine, smaller than particles of smoke, and that the planet itself is likely a small, mercury-sized body rich in volatile minerals that vaporize easily. Its ultimate fate is written in its own tale. The erosion rate is staggering, with models suggesting the entire world could be ground down to nothing within 100 million years, a blink in cosmic time. This forces two profound and humbling questions. How many other close-in, rocky worlds are undergoing this same slow, dusty dissolution, their transit signals too subtle or variable for us to yet detect? And what does this teach us about the final stages of planetary evolution for worlds that dare to orbit too close to their suns? KIC 12,557,548b is a planet in the act of becoming a memory, a world turning into its own funeral shroud, offering us a fleeting glimpse of a celestial process that is usually the quiet end note of a billion-year story. From this vision of a world dissolving into dust, we turn our gaze toward a planet that does the opposite, a world that reflects nearly all the light that touches it, shining like a perfect mirror in the void. A world of perfect reflection gleams in the darkness, a polished sphere defying its own infernal heat. LTT 9779b is an ultra-hot Neptune, a planet so close to its star its dayside temperature soars to over 3,000 degrees Fahrenheit, yet it reflects a staggering 80% of the light that strikes it. This extraordinary geometric albedo, a measurement of its mirror-like quality, was captured by the European Space Agency's CHEOPS mission, and it presents a stunning paradox. How can a world that should be absorbing nearly all stellar energy, glowing like a blacksmith's forge, instead act like a celestial disco ball? The answer seems to lie not in its surface, but in a sky of alien metallurgy. Data suggests the presence of a permanent, global cloud deck, but these are not water vapor or even silicate clouds. At such blistering temperatures, experts analyzing the CHEOPS findings propose the clouds could be composed of condensed metals like titanium or aluminum, or exotic silicate compounds like enstatite. These metallic vapors rise from the scorching depths, cool just enough at a specific high altitude to condense into brilliant, reflective droplets, and form a seamless, shiny blanket that covers the entire dayside. This creates a powerful energy balance. The clouds reflect a huge portion of the incoming stellar radiation back into space, preventing it from heating the deeper atmosphere. Yet the planet is still intensely hot because what little energy is absorbed, combined with internal heat, is then re-radiated as thermal emission. It is the difference between wearing a black shirt and a polished silver suit on a sunny day. One absorbs the heat, the other deflects it, though both will eventually warm in the environment. To visualize this, picture a ball of liquid mercury held over a blowtorch. The surface would remain a shimmering, perfect mirror, even as the intense heat beneath tries to make it glow. This world maintains that same impossible state on a planetary scale. Why don't all hot planets develop such brilliant shields? The precise cocktail of atmospheric composition, temperature gradient, and global circulation must align perfectly. If the atmosphere lacks the right heavy elements, or if the vertical winds are too weak to carry vapors to the condensation layer, no reflective blanket will form. The climate consequences are profound. By bouncing so much energy away, these metallic clouds act as a powerful thermostat, potentially capping the maximum temperature the lower atmosphere can reach and dramatically slowing the process of atmospheric evaporation that dooms other hot worlds. This glinting anomaly forces us to reconsider the very tools we use to study distant planets. A highly reflective world can appear deceptively cool in certain observations, potentially hiding its true nature from our initial surveys. It also expands the canvas of possible planetary aesthetics, revealing that the cosmos holds not just dark charcoal worlds and blue glass rainstorms, but also brilliant metallic orbs shining with borrowed light. Having journeyed from evaporating giants to diamond cores, from triple suns to mirror planets, these 25 anomalies collectively reveal a universe of breathtaking diversity and relentless creativity. They are not mere curiosities, but fundamental challenges to every assumption we have ever made about how planets form, evolve, and behave. Each one is a testament to the fact that for every rule we derive from our quiet solar system, the galaxy writes a spectacular exception. They teach us humility, showing that our understanding of physics is not wrong but incomplete, constantly being rewritten by the data streaming in from the darkness. Most importantly, they ignite our sense of wonder, proving that the cosmos is far stranger, more dynamic, and more wondrous than we ever dared to imagine from our small, blue vantage point. The search is far from over, for every mystery solved unveils 10 more waiting in the starlight. These 25 worlds are not random cosmic accidents, but a pattern of defiance that reveals a deeper truth. Our universe is a laboratory of extremes, where the most bizarre conditions are not just possible, but a regular feature of planetary evolution. Each anomaly, from the evaporating tail of KIC 12,557,548b to the metallic mirror of LTT 9779b, represents a natural experiment, testing the laws of physics under stresses we could never replicate on Earth. When we step back, common threads emerge, weaving these individual wonders into a single, breathtaking narrative. The most powerful force shaping these oddities is extreme stellar proximity. Worlds like WASP-12b and the ultra-short period planets show us that a star's embrace can be a destructive kiss, boiling away atmospheres, melting surfaces, and stretching worlds into teardrops. Yet, this same ferocious energy also drives the exotic chemistry we see, vaporizing silicates into glass rain or metals into reflective clouds. It is a reminder that a planet's environment is dictated first by its sun, and our own placid solar system may be the cosmic exception, not the rule. Gravitational chaos is the second great sculptor. The flipped orbit of HTP 7b, the polar path of XO 3b, and the wild eccentricity of HD 80606b are all gravitational scars, permanent records of a system's violent youth. They prove that planetary systems are not born in orderly arrangements, but often undergo periods of dramatic rearrangement, a celestial billiards game where worlds are slingshotted, captured, or torn apart. This reshapes our entire timeline for planetary evolution, suggesting that calm, stable orbits like Earth's are a hard-won prize, not a default setting. Furthermore, these gravitational interactions often leave behind the very materials for new wonders, perhaps scattering the heavy elements that would one later form a diamond world or disrupting a moon to create a colossal ring system. The third thread is the stunning diversity of exotic chemistry and states of matter. Our traditional categories of terrestrial and gaseous planets are hopelessly inadequate. We must now make room for water worlds with global oceans over hot ice, mega-Earths of compressed rock and metal, and puffy giants of incomprehensibly low density. The atmospheric recipes alone range from clear skies of sodium to global hazes of titanium dust. Leading astrophysicists note that each new discovery forces a refinement and sometimes an overturning of long-held theories. The forbidden planet NGTS 1b challenges core accretion, while the potential captured rogue HD 106906b questions where a planet's story can begin. Our classification systems are straining under the weight of this diversity, pushing us toward a new language that describes worlds by their processes and histories, not just their size and orbit. This revolution in understanding is powered by a parallel revolution in technology. The Kepler mission's relentless photometry, the Hubble Space Telescope's spectroscopic eyes, and the direct imaging power of instruments like the Gemini Planet Imager have turned theoretical possibilities into measured realities. We are no longer just detecting planets. We are beginning to take their weather reports and analyze their atmospheric chemistry from hundreds of light years away. The future promises even deeper insight. The James Webb Space Telescope, with its infrared sensitivity, is poised to peer through the cloudy shrouds of worlds like GJ 1214b, potentially confirming the first true water world or identifying the molecular building blocks of alien atmospheres with unprecedented clarity. Future missions will directly image Earth like planets around nearby stars, searching not for anomalies of extremes, but for the subtle signatures of stability and perhaps life. So what fundamental laws might we still be missing? These anomalies suggest our grasp of material science under ultra-high pressures, the intricacies of atmospheric dynamics on global scales, and the full spectrum of magnetic dynamo generation is still elementary. Viewing the cosmos as a laboratory means every strange world is a data point, helping us write a more complete and humbling textbook of universal physics. The ultimate implication is that for every rule we think is solid, the galaxy has crafted a spectacular exception. This journey through planetary extremes does not just catalogue curiosities, it expands the realm of the possible, forcing us to dream bigger and question more deeply about what lies in the quiet darkness between the stars. This grand tour of cosmic oddities is far more than a list of records. Every world we have encountered, from the disintegrating dust cloud of KIC 125575448b to the glittering diamond heart of PSRJ 1719-1438b, serves as a direct challenge to the textbooks. They are not exceptions to the rules of physics, but vital demonstrations that our rules are still being written, shaped by data from the most extreme laboratories imaginable. These anomalies force a humbling and exhilarating realization. Our own solar system, with its neat orbital planes and clear categories of planets, is a single, quiet chapter in a much wilder galactic story. The universe operates on a canvas of staggering scale and diversity, where the conditions for forging a world are as varied as the stars themselves. What we once considered the outer limits of possibility, a planet with 3 suns or a year lasting mere hours, is simply another Tuesday in the cosmos. This constant revision is not a failure of science, but its greatest triumph, a sign that our curiosity is pushing further into the unknown than ever before. Each bizarre discovery refines our search, telling us where to look next and what questions we have not even thought to ask. They remind us that wonder is not the opposite of knowledge, but its essential fuel. The next time you look up at a clear night sky, remember that the darkness between those points of light is not empty. It is filled with possibilities we are only beginning to grasp, a tapestry of worlds where iron snow falls and mirrors gleam in perpetual stellar fire. Our journey does not end here, it merely points the way forward. If this voyage through the universe's strangest wonders reshaped your view of reality, let that curiosity continue. Your engagement helps bring these distant mysteries closer. Consider liking this video to support this channel, subscribing for more deep dives into the enigmas of space, and sharing your own thoughts below. Which of these 25 anomalies left you the most awestruck, and what do you think we will discover next? Thank you for exploring the edges of understanding with us. Until our next journey into the unknown, keep looking up and never stop wondering.